At this point, we want to apply forwarding to our hardware. And to do this, we need to answer two questions. The first question is how to detect when to apply the forwarding. And the second is how to implement it. So it's about detection first, and then implementing. So let's consider this sequence. We have subtract with row hazard on S2. And you notice that we write here and we read in all the four different instructions here and here and here and here. So to be able to understand how is this happening and why do we need the forwarding, let's check it in this slide. This is our 5 instructions, and this is register number 2. To forward, to make sure that all the other instructions have the correct value of S2, we need to get it from the write back register and feed it to all the register reading stages of all the instructions. As you know, we cannot have a backward line in a timing diagram. This means that we are going to the best. So this is not allowed. This is also not allowed. This line here is okay. And notice the benefit that we gained from having the write happens in the first cycle of the register file, and or the first half cycle, and we read in the second half cycle. So we write here and then we read here, and this line was okay. This one is also okay, and those two instructions won't have any problem, and they don't actually need any kind of forwarding. The problem happens when the backward lines, those two lines. So to do this, we will use the forwarding, which means that we will get the result as soon as we can. We know here we can forward from the ALU to the ALU because the result of the subtract would be ready here and needed as an operand right here. So we forward it. For the OR instruction, it needs the register 2 as the second operand right here. And it could have it from the output of the subtract instruction, but you need to first save it in the pipeline register and then move it along the subtract instruction when it's moving to the second memory to write back pipeline register, and from that you can get it as the second operand by pipeline. Notice that the red line here is forwarding from ALU to ALU, and the green line is forwarding from the memory to ALU. Now we want to be able to detect the need to forward. And to do this, we need the RS and the RT, which are the operands that you read, that reads the register. So the reading happens here, and you need to compare it with registers that writes. So you need to, this way you detect the row hazard. So those two will read the registers, and you need to compare it with other instruction that writes it. So if this happens, then we have a row hazard. The write happens first, and then the read follows. So if this is the RS and the RT coming out of the ID to execute pipeline register, we know that the data hazard could be removed if we forward from the this pipeline register, the execute memory register, meaning that we are forwarding from the ALU back to the ALU. The other way, which is this way, we are forwarding from the memory back to the A. So what happens is we compare the RS and the RT because the forwarding could happen in the first operand or the second operand. So we compare the RS with the destination register from the execute memory pipeline register, which is this one. So we compare its RD with the RS and the RT. So if they are equal, then the pipeline is the need for the pipeline for the forwarding is detected. So now we have a forwarding unit that needs the RS and the RT, and it also needs the RD that comes from this pipeline register to be able to make those two comparisons. This way we cover the forwarding from the ALU back to the ALU again. So notice that we are forwarding back and we are moving this to those inputs of those new muxes. These two new muxes, either it gets the normal behavior or the forwarding from the ALU. This will be, if this is 0, 0, this is 1, 0. So this is going to be 0, 1, and this one is going to be 0. Or the other way is forwarding from the memory write back pipeline register, which means that you are forwarding from the memory to ALU. So you forward it this way. Notice this line below, and then you go up here and here. This will be 1, 0, and this will be also 1, 0. And this happens when the RD of this pipeline register, which is the memory write back register RD, being the destination register, is equal to the source register RS or the source register RT, which are these two. This way you detect the pipeline. So let's have a close look to forwarding unit. The forwarding unit has as inputs the RS, the RT, the RD of this pipeline register, the RD of this pipeline register, and based on these comparisons, it tells you to forward because it sends the right multiplexer selectors to select either this or this one. And notice that this could happen in the first operand or the second operand. So now we covered the first part of detecting the need for forwarding. Also, you only forward if you are writing to the register file, meaning that the register write control is asserted or active. Whether it's in the pipeline register execute memory or memory/write back, meaning that you are forwarding from ALU or forwarding from memory. You check the register write and make sure that it is equal to 1. Also, make sure that you are not updating the register 0. It's not allowed. It's having the constant 0. So make sure that the destination register doesn't equal to 0. This way, you know that if you have the need to forward from the execute, the register write is active, and you are not updating the 0 register, and the RD is equal to RS, then you forward. Similarly, for RT, you also forward. But here we have forward A and forward B, because forward A is the first related to the first operand, and forward B related to the second operand. And this is what we have here. This is forward A for the first operand, forward B for the second operand. And now by working on the forwarding from the ALU back, we are having those two lines selected as an output, which is 0 and 1, 0 and 1. And this is what we have here. Now from the memory, we have the same way. You notice the similarity. The only difference is that now we are checking the other pipeline register, indicating that we are forwarding from the memory to the AL. Also, you have the different combination of the inputs of the multiplexers, because now we have 1 0 here and 1 0 here. Now, you think that this is okay, and now you are able to detect correctly. However, consider this hazard, which is called double data hazard, meaning that now this is a write, and you read it here, and then you update it, and now it becomes a write, and then you read it again. So you have two hazards back to back, and you want the most recent value. And to be able to do this, we will update our conditions. We are adding these two lines, these purple lines, which means now the forwarding from ALU to ALU it's not affected. Only the effect happens if you forward from the memory back to the ALU. You need to make sure that the conditions that we discussed are valid, and also you are not already forwarding from the execute. So if you are not having this valid, you can see the not here. And this is also similar if you are doing the other operand. This is the first operand RS, and this is for the RT. So you need to make sure that you get the most recent the most recent update by making sure that if you are trying to forward from the memory to the ALU, make sure that you are not already having that in the from ALU to ALU. Now the data path is updated now, and we added the forward unit, and notice that we have RS and RT. Those are source. These are the source RS and RT. Notice that we are repeating the RT because the RT sometimes it's a source, sometimes it's a destination. So here the RT is a destination, here the RT is a source. For detecting forward, we care about when the RT is a source. And this is why we have the RS and the RT as input to the forwarding unit. Also, we have the RD and the RD, one time from this pipeline register, the other time from this pipeline register. Now we added those two blue lines, the control lines coming from the controls, to make sure that the register write is active. This is we are getting it from the write back here, and we are also getting it from the write back right there. And we give the outputs to the muxes. This way, we detect the forward, and we can do it without a problem. Now, notice here, if you detect the forward, you just get the operand this way, and no need to add any additional stalls or bubbles. And the reason is, our example, we have from R type to another R type. Similarly, the first example here, from R type to other R types. But what if we have a load? The load, we use the load, use data hazard, we use forwarding, and even with that, we need to add a stall. Notice what happens if you have a load followed by the and other instruction that needs the S2. What happens for the AND, you will get the result of the load as soon as you could here, right here. And you need to supply it for the ALU of the AND instruction in the previous cycle. So you are going against time. You are going to the past. So what happens? Now you need to stall for one cycle. So now we need to update our hardware a little bit more to make sure of this case. When we have a load followed by R type, we don't only forward, we forward and add also a stall cycle. So you check when using an instruction is decoded in the ID stage. The ALU operand register number in the ID stage are given by the RS and the RT, as we know. So these are the source registers, RS and RT. If you have a memory read, if you have a memory read active, this means that the instruction is loaded. And you have the source registers equal to the destination register. And notice now the destination register is RT, not RD, because this is a load instruction. So if this happens, then we detect, and we also not only we detect the need for the forward, we also need to stall or insert a bubble. How to stall the pipeline? To stall the pipeline, meaning that you are adding a no operation or you are adding a bubble. To do this, you need to do 2 points. The first one, you force the control values of the subsequent cycles to 0. So the execute, the memory, and the write back, all of them will do no operation. And then you prevent the update of the program counter to keep the current current instruction one more cycle. This way you add the stop. So using an instruction is decoded again, you following instruction is fetched again, and one cycle stall allows the memory to read the data for the load correctly and forward it without problem. And this happens this way. What happens is we make the controls of those 3 cycles of the next instructions no operations or not. This way we are adding the bubble here, or we are inserting one stop. So the AND becomes a NOP, this one. And after that, you repeat. This is the first thing. We inserted the stall this way. And the second point, you notice that we repeat the ID for using instruction and refetch the one after it as well, resulting on a new fetch right here. So the fetch that was supposed to be here is no longer here. It is now here. And this way you have a bubble. And then you have this one is fetched, decode, executed, and then memory, and then write back. The next one becomes a NOP. So it's no operation. It's a bubble here. And now this one, you can fetch it right here. What you did is actually you copied the fetch that happened before, because you fetched it already here, but it failed. So you moved it back. So you can do the fetch and then decode, execute, memory, and write back. And the last one, you do the fetch here, decode, execute, memory, and then write back, and you continue. You notice that you weren't able to do the fetch of the AND right here. You pushed it one cycle to this position, and this way you do it. To apply these changes in the hardware, we do it this way. Now we have a new unit, which is called the hazard detection unit. We had the forwarding unit before, and now we have the hazard detection unit in case we have a load. So what happens? Notice that we have the RT. When the RT is a destination, here the RT is a source, but here is the destination. when it is a destination, and also the memory read is active, meaning that the instruction is load, we also take some information from the instruction to know if the forwarding is valid. And once this is correct, you supply the control with 0. So this way you make the write back, the memory, and the execute, and this pipeline register zeros, and here, and also here. So notice the control, either it passes normally, and now we are adding a multiplexer, and it has an output from the hazard detection if the load happens, which means, let me go back. This means that the memory read is active and the RS is equal to RT. The RT or the RT is equal to the RT. So if this happens, this is the job of the hazard detection unit. If it knows that, then it will make this mux selection to be 0. So it will zero out all the controls on all of these. This way we inserted the bubble. So also notice here that those two lines is actually the RS and RT. The RS and RT to be able to know that this is actually a load. The other point is we need to make sure that the BC is frozen. So it's not updated. So we need to make sure that the BC write doesn't happen. And they also update this pipeline register. So this hardware is actually implementing those 2 points. The first one, we applied the 0 on the control, making it doing no operation. And the second, we prevent the updated of the BC and the IFID register. And these are indicated by those 2 lines. Now, at this point, we fixed all the row hazards, whether it's from R-type to R-type or from load to R-type, by adding those hardwares. The first is the forward unit, and the other is the hazard detection unit. Now, the stalls reduce the performance, but are required to get the correct result. The compiler can arrange code to avoid hazards and stalls, which require knowledge of the pipeline structure. These are the costs that we need to pay to make sure that the pipelines work. Now, we finished the row hazard, but still we have hazard that could be, or stalls that we need to add if we have a control hazard that comes from branch. And this is what we are discussing now. So in branch hazard, if the branch outcome determined in the memory stage, which is far back or far away inside the pipeline stages. So if that's the case, then you will be able to know the branch outcome right here. So if there is a branch instruction that started from this position 40, this is the instruction address. The address is 40, and then you add 4, and then you add 4, and then you add 4. But notice there is a big jump here. This is 72, because this is a branch instruction, and if the branch is taken, then you will add the offset 28. You will add the offset 28. Note that we added the 28 to the 44, which is BC plus 4. So 44 plus 28, this equals to 72, which is the address of the instructions from the target. So basically what happens here, we know that the outcome, we know the branch outcome right here. So all the instructions that we fetched here and here and here, we need to flush them out, meaning that we insert a bubble a bubble and also a bubble, because they are fetched incorrectly. And the reason is we didn't know the outcome until later, deeply inside the pipeline. And then you fetch the correct one at the end. So what happens? We will move the hardware to determine the outcome to the ID stage. To do this, we need a target address adder. We need to move it back to the ID stage. And we need also a register comparator that we need to include. This is a new hardware we need to include in the pipeline. So by having the same example, the branch in address 40, there is an instruction before that. And this is the branch followed by and, or, and whatever. And then this is the target at 72. Now, by applying this, which means that all the instruction, the branch outcome, we know it at the end of the ID stage. What we will do in the hardware is now we will include this adder, or actually we moved it back from the memory all the way back to the ID stage. And notice if the branch is here, followed by the AND, this is the subtract instruction that was the first instruction, followed by the branch, followed by the AND. Now what happens here, we have 44, which was saved in the pipeline register if/ID, and you add to it the immediate value, which is 7. 7 is actually shifted to the left by 2, which means you are multiplying it by 4. 7 times 4 is 28. And now you add 28 with 44 and you get 72. And this way, you know that you should have 72 as the next instruction. But notice that you know all of this value once you're done with the ID stage, once you're here. Because you calculate the target address within the ID or within the decode stage. And also you compare the registers. Look at this is at the end of the ID or the decode stage. So we added this hardware that compare the registers 1 and 3, since we have 1 and 3 here. So this is the hardware that we added here and there. This one we moved it, and this one we added. This is a new hardware to compare. So this one, this example, if the branch is taken, this is what will happen. And notice when we were calculating for the branch, we already fetched the AND. And now the AND, because the branch is taking, the AND is incorrectly fetched. So what happens in the next cycle, we will have the branch moving to the next stage from the ID, it moves to the EX, or from the decode to the execute. But the AND now is taken out, the old AND, which is this one, is taken out, and instead we have a bubble. And then you get the new instruction from the target, which is the load instruction. Now, the data hazard for the branches. Now we finished the control of the hardware that we need to add for the control hazards. But what about the row hazards that could happen between instructions that is before the branch? Notice the branch need 2 source registers to compare. What if the register 1 and 4 is actually an output, and this is usually the case actually. They are written in registers in a previous instructions. So you have an add followed by that. If those 2 instructions for the 1 and 4 are the destination of the second and the third preceding ALU instruction, then that's fine. you can forward them without a problem. Notice that this one here, for the comparison, the branch expecting the one register number 1 and register number 4 in the ID stage now. So they need to be supplied to the ID stage from these instructions. And the add, you could get it from here, from the execute, and feed it to the ID. And for this add, you can get it from the memory and this ID. Notice that there is another instruction here. So this way, you can resolve the problem using forwarding, and the problem would be solved. Now, what if the comparison registers, now we have 1 and 4, is a destination of preceding ALU instruction, the preceding, or the second preceding load. This means that the branch originally was here. And right before that, we have the add for the 4, register number 4. It's written in register number 4 of the add instruction. And the one we had the load. This way, if this is what happens, because of these reasons, you need to add the bubble. So you take out the branch and you put it here. Because you need to calculate the branch outcome and checking or comparing the registers and getting the target address in the ID stage. And you need to get this from the execute stage and for the load from the memory stage. So you need to add the bubble. So basically, if they are directly before the branch, the add and the load, then you need to add one bubble, or you need to add one stall cycle. Now, what happens if the comparison register is the destination of immediately preceding load? So the branch originally was here. This was the branch. And there was one of the register that you need to compare, which is 1, is the output or the is written to the register number 1 of the load instruction. So you have load and following the load, the branch right away. So what happens is the load will have the value here, and you need to supply it to the ID stage. So you need to stall 2 times to make sure that the ID stage here. To check this, simply put F D X M W again, F D X M W again, F D X M and W, and the last one. Sorry, this one is written incorrectly. This is fetch, decode, execute, memory, and write back, and then fetch, decode, execute, memory, and write back. So what happens? You know the load will have its value here. When can you supply it to the decode? You can't supply it here. This is memory, not decode. You can't also supply it here. This is execute. You only can supply to the decode right here, which means this one and this one should be balanced. This way, you know it. So you stall the branch 2 times if the directly preceding instruction is a load instruction. If the load wasn't directly, there was another instruction in between, then you need only one stall. Now, scheduling the branch delay slot. The delay slot is the instruction following the branch. So if this is the branch, we write it in high-level language, but it's similar behavior. So if this is a branch, the delay slot following it directly. Similarly, this is the branch, the delay slot following it, follow that, and this is the branch, the delay slot following this. So this delay slot could be a no operation. So we need to fill it with other instructions to not waste time. So one way, and the best option, is to have an independent instruction from before the branch and you plug it in the delay slot. So you take this one and you plug it in the delay slot. This way is the best way, and this way you won't have any problem or worrying about adding more stops. If this doesn't, you can't do it, you can't get an independent instruction and put it in the delay slot, then you have two other options. Either you get an instruction from the target. So if you are going back, if there is a branch you go backward, then you get this one and put it in the delay slot. Or you get an instruction from the fall through if you are going this way. So you get an instruction and you put it in the delay slot. We took this one and we put it in the delay slot. These are the three options: from before, from the target, or from fall through. This is the best, and you should focus on this first. If this is not available, then you can do this for us. Now, the dynamic branch prediction in deeper and superscalar pipeline, the branch penalty is more significant. It has a lot of cost. So one way to make the branch hazard or the control hazard lower is by prediction. And we said before that we have two types, static and dynamic, and the dynamic prediction is better than static prediction. So we will take two simple examples. The first one is a 1-bit predictor. And to know the 1-bit predictor, here's the figure that shows you have a program counter, and you should have the 1-bit counter or the predictor as a history here. So for each branch, you should have a history for it. So you have 1 bit stored here. If it is 0, not taken. If 1, then the branch is taken. That's it. So also with the history, you have the buffer target, the branch target buffer, or the BT. And this is the reduce the cost of having to calculate the target address each time you have a branch. So instead of recalculating every time this happens, you calculate it once and then you store it inside this buffer. Now, if the branch is taken and you know the target address, then if it is a hit, this will be supplied to the selector line that tells you that you need to take the target address and go fetch the next address this way using this target address. Otherwise, you just do the BC plus 4 or the BC plus the instruction. So using the dynamic prediction, the branch prediction buffer or the branch history table should be filled for each branch. So let's focus only on one branch, which means that it's 1 bit, because this is 1-bit counter, 1-bit predictor. So it's a 1 bit for in a big vector. This vector, this one, for example, it has many places or many locations. This location for one branch, this is for another branch, and this is for our branch. So it's indexed by the recent branch instruction addresses, stores the outcome, is it taken or not taken. So basically the 1-bit predictor, if previously the branch was taken, then the next prediction is taken. If it is previously not taken, then the next prediction is not taken. Now, to execute the branch, you check the table, expect the same outcome, and then start fetching from the fall through or the target. Because now, if this is taken and it's a hit, then you get the target address and you start getting the instruction from the fall through or the target. Now, if your prediction is wrong and this could happen, then you flush the pipeline and flip the prediction, which means since it is wrong, if it was taken before, then next time it would be not taken, and vice versa. To show the 1-bit predictor, this is a simple way of showing it. This makes it easier for you to remember it as well. You change prediction on a single misprediction. So if your prediction, your current prediction is not taken, and actually it was not taken, so your next prediction is going to be not taken. Now, if your current prediction is not taken, and the actual are the ones in the arrows, and the actual was taken, then you will predict taken next time. Now, if your current prediction is taken, and the actual is also taken, this is good. So it's matching, and the next time you also predict taking. Now, if the current prediction is taken, and unfortunately the actual was not taken, which is a wrong prediction now, or misprediction, then you go back to predicting not taking next time. And this satisfies what we say here. You change the prediction between not taken and taken only in a single misprediction. So notice this movement happens if they don't match. This movement happens if those do not match. Now, consider this example. If you have the following sequence of actual outcomes, these are actual outcomes for a single static branch. So the branch outcome was taken, not taken, not taken, and so on. Using 1-bit counter that is initialized at the beginning as not taken. Which of the branches in this sequence would be mispredicted? How to do this? You need to fill up this table. So at the beginning, your prediction was not taken, and the actual was taken. So your next prediction would be taken, which is actually this one. You copy it here, and you keep copying again. Actually, you fill this one again right here, beginning from the second one. So taken, not taken, not taken, and so on. So you copy it again. This is the 1-bit predictor. It works this way. Now you see if there is misprediction or not. How to know this? You compare this with this. You know they are different, so there is a misprediction here, which is bad news. So yes, there is misprediction here and here too. So these are the mispredictions when they differ. And you can see that this is a lot of misprediction. And the reason is, it's like you're saying that 1-bit predictor is not enough or premature. And this is one way to show the 1-bit predictor shortcut. If you have 2 nested loops, where you have an inner and an outer loops, the inner loop branches actually is mispredicted 2 times, one after the other. How? First, you mispredict as taken on the last iteration of the inner loop. So this is the inner loop, you go this way, and in the last one, you're thinking that you are going back, because in the loop you move a lot of iteration this way. So in the last one, you think that you are going again to this label, but it's not taken. So you predict it as taken, but the actual is no, it's not taken. So that's the first misprediction on the last iteration of the inner loop. And then after that, you go to the outer one. And you do some work in the outer one, and then you go back again to the inner loop. Last time you said that the prediction was incorrect. So you will change it in the 1-bit predictor. A predictor. What happens? You mispredicted as taken. So you said that it is taken. Let's say it is 1, equal to 1. But the reality, it was not taken. Now you change it to make it 0. That's the first misprediction. Now, after you go to the outer loop and go back again you will mispredict it as not taken. Because now the history says 0, which is not taken. But when you go in the inner loop, it's actually taken. So this is also misprediction, and you will change it to 1 again. So basically you have 2 misprediction. One time in the last iteration of the inner loop, and another time on the first iteration of the inner loop, the next time around, the direct next time around. And it's like you are changing between taken and not taken too quickly. And one way to rectify this is by using the 2-bit predictor, where you only change the prediction in 2 successive misprediction. And this is the state machine for it. This is the predict taken, and the other one is also predict taken, but to show the difference, this is a strong predict taken, and this is a weak predict taken. This is a weak not taken, and this is a strong not taken. So in the strong predict taken and the weak predict taken, both of them, the prediction is taken. And these two, both of them, the prediction is not taken. However, the change is a little bit different. So if your prediction match the actual, then you go back to the same state, or the same prediction. If your prediction match the actual, again, you go back. But if it doesn't match, then you go to the next prediction. So this prediction, you predicted here taken, strong taken. If it is not taken, the actual, then you go to the weak taken. If it's also, again, not taken, then at this time, it was not taken. The misprediction happens 2 times. And because of this, you move from this weak taken to weak not taken. Now you are here. If it is not taken, then you continue moving and you move to the strong not taken, because you have 3 misprediction. But notice the change from taken to not taken happens in 2 misprediction. This is the first one, and this is the second one. So note, we talked about these black arrows. For the blue, it's the same. If you predict not taken and the actual doesn't match, you go to the weak not taken. Again, doesn't match, then you go to the weak taken. And at this point, if they also, if it is taken, then this is good news, and go to the strong taken. So you know that now you understand what we mean by it changes the prediction in 2 successive predictions. Most of the cases, your prediction is either here or here. So you will change from here to here if you have 2 mispredictions. You will move from here to here. Sorry, from here to here, if you have 2 mispredictions. But from here to here, you will have, if you have 3 mispredictions. Actually, this is a misprediction. Movement from here to here, this is 1 misprediction. From here to here, another misprediction. But from here to here, you are predicting not taken, and it is actually not taken. So this is not a misprediction. This one is a misprediction, and this one is a misprediction. But this one is not, because it's matching the same prediction. Then you predicted not taking, and the actual is also not taking. So it only changes the prediction if you have 2 successive mispredictions. Now calculating the branch target. Even with the predictor, still you need to calculate the target address, and this could take some penalty. And to get away from this penalty, one way is to cache the target address. And we do this by the buffer that we introduced before in the first figure. Calculating the branch target, we don't know if the prediction is the right one. It may have been put there by another branch that has the same lower order address bit. So you think you have the same branch, but it's not. It's something that has the same lower order, the low order address. Also, whatever prediction you make, there is a chance, hopefully a low chance, that your prediction is incorrect. And if this happens, then there is a penalty of flushing the pipeline and adding stalls. Now, at the end of this chapter, the processor chapter, we have these fallacies. Sometimes you think pipelining is easy. The basic idea, yes, it is easy, but the devil is in the details, such as detecting data hazards, and you see that we talked a lot about it. Sometimes we add one. Let me list it for you. For the row hazards, if from low or load word to R type, then you add one. You do the forwarding and add one cycle. For the branch, which is the control hazard, if you assume that all the calculation happen in the ID stage, now, if that's the case, then you need to add one stall right after the branch in case if your prediction is wrong. So if the prediction is wrong, you need to add one stall cycle. So let me call it one knob here, and we call this one knob. These are the main 2 points that we need to add the knob operation, and we also need to make sure that we know exactly when to detect the need for the forwarding and how to manage the stalling the pipelines by adding these knobs and so on. Also, we discussed what happens before the branch equal. So if you have a branch equal, and if you have a branch equal, and before that, we have a R type, let me call it R type, then you need one knob inserted here to make sure that the R type supplying the branch equal. If there is a dependency, of course. If there is a load right before the branch equal, then you need not one knob, you need 2 knobs. So that's the cases that we discussed. So the devil is actually in the details. Pipelining is independent of the technology. So why haven't we always done pipelining? More transistors make more advanced technique feasible, and the pipelining related ISO design need to take into account the technology trends, such as the predicated instructions. And if you are interested, read about this. It's actually having some good techniques. And as a pitfall, you think the pipeline is easy to be implemented everywhere, no matter what's the ISA, but actually the poor ISA design can make the pipelining harder. So if you have a complex instruction set, like these two, you will have to do a lot of work when you work with pipelining. Also, complex addressing mode makes it harder to deal with the pipeline. Register updates side effects, and also the memory and directions are not easy. And the delayed branches, the advanced pipelines have long delay slots instead of only one. If you have a very complex ISA, probably you have multiple delay slots, and this needs a lot of work. Because MIPS is easy, the pipelining MIPS becomes manageable, and you can do it without trouble, and you take care of whatever hazards or problems that you are facing in the hardware. At this point, we finish the chapter, the first major chapter of the computer organization and architecture, which is the processor. And next time, we will talk about the second major chapter, which is the memory.